So if you want to show those steps, go ahead. You start here. You will multiply both sides by 2. You will reverse from here, right? So you have to change the 2 into the absolute value. Then you're going backwards with the property. Then you're using this. And then you have to change -2 into -5 plus 3. And then identify that this is, show that this is the function and this is the limit in absolute value less than epsilon. If you want to do that, I'm fine.
So let me ask you, in order to receive full credit, do we have to show both parts or not?
That's what I said. This is for full credit. That's all I said 3 times, right? That's all I want you to show. If you want to reverse, go ahead. But if you don't write this sentence, at least this sentence, then you cannot get full credit. I'm super happy with this sentence.
Because essentially it takes the place of the last half of the proof, right?
Exactly. By writing this, then I know that you know what you're doing, and I know that you can reverse those. I don't want you to spend the time and reverse them. If you think that you should reverse them and not just write this sentence, I'm fine with either one. But at least this sentence has to be put in writing. It's up to you if you want to perform those steps or not. But I'm happy if you just say, show that delta equals epsilon over 2 works by reversing the steps from above. And I'm super happy with that sentence. Good enough for full credit. Is that okay, everyone?
I like that.
Yes. Gia, is that okay now?
Yes.
Perfect. Excellent. Okay, so let's show another proof and move on because we have a lot of work. Okay, so can anyone dictate now, please?
Epsilon.
For every epsilon
Greater than 0.
Excellent. We will find there exists
Delta greater than 0.
Excellent. Such that. Very good. Great job so far. Mickey, would you like to continue such that? Mickey, are you with us? Hello? Well, if you want to come back through your phone. Okay, such that. Isaac?
I don't know how to say it in words.
Just to tell me how to write it.
Okay. 0 is less than.
Excellent.
X.
Something is very important that is missing.
Absolute. The absolute.
Very good. Awesome.
Of x minus 5.
Excellent. Awesome.
Less than delta.
Excellent. Awesome. Derek, will you continue?
The absolute value.
Excellent.
Of 3x minus 1/2 minus 7 is less than epsilon.
Excellent. Brilliant. Thank you, guys. Excellent. Where do we start? Where is our starting point? Great job. Very good. Trey, how do we start?
Simplifying for epsilon.
Say it again.
Simplifying the formula.
So can you just dictate?
3x minus 1. Sorry.
Okay. So that's indeed our starting point. Awesome. Josh, what do you think? What is the next step?
We are supposed to simplify. So 3x.
Here's your hint. What am I getting at?
Yeah, I don't have a clue.
Wait, I have a question.
Yes.
So in the original equation, it's the limit of 3 halves x minus 1 half as x approaches 5. Why did we get rid of the 2 in the denominator of the x value?
Oh, I just forgot about it.
Okay, I got really confused for a minute.
You cannot. It's just an error. Oh, my fault. I should have checked. Okay. Very good. Thank you so much. Okay, Sarah, what am I getting at? What am I really telling you with that?
You have to convert the -7 into 14 halves.
Okay, so you're saying we have to find the least common denominator, which is 2, and then we write 3x minus 1, right? And minus 14.
Yeah.
Excellent. Great job. Next, Carson.
You would then use the absolute value rule to say that the absolute value of 3x minus 1 minus 14.
Oh, I have to simplify that. I cannot say minus 1 minus 14.
It's gonna be
Minus 15.
Very good. What is the next?
Put that over.
What is the next step?
Sorry.
Go ahead.
We have like 3 parentheses x minus 5.
Excellent. What is the next step? Nabiha, what do you think?
Do you do absolute value 3/2 times absolute value x minus 5?
Perfect, but in this particular way, separate each factor. Good. Okay. Yen?
Would you plug in after that?
I don't have anything to plug in. This is not an evaluation type of situation. We're not plugging in anything. Oscar, what do you think will be the next step?
I thought we were done there.
Say it again.
No, I thought we were done. Aren't we supposed to use somewhere in there the delta sign?
Okay, what is what we are not there yet. What is the next step? Mark, will you help us?
I was thinking about multiplying each side by 2.
Of course, but first I have to eliminate the absolute value on these numbers. I have to clean it up. So I have to write 3, the absolute value of x minus 5 over 2 less than epsilon. I cannot continue before doing that. And now we have to get rid of 3 halves. We are in calculus, let's get rid of 3 halves in one step. We need to multiply both sides by Jordan?
2/3.
Exactly. So then what do I have on the left-hand side? Gabriel?
Absolute value.
Of x minus 5, because that was my target. It's right here. This is my target. If I don't get the absolute value of x on the left, then I will not be able to find delta. Good. So then what do we have on the right-hand side? Anyone?
2/3. Yeah,
Say it again.
Epsilon, 2 epsilon over 3.
Excellent. So can anyone now identify delta for us? Leonardo?
I'm sorry, what was the question?
Yes, let's identify delta. How much is it?
I'm not too sure, to be honest.
Can anyone help us identify delta?
Is it 2/3?
Delta equals.
Very good.
Epsilon 2/3?
That's it.
Epsilon.
That's it. And in step 2, reverse. The steps to show that delta equals 2 epsilon over 3 works. So maybe not everyone understood this perfectly, but initially it looked like gibberish. But now I think you're understanding every step. Would you agree? Would you disagree?
Agree.
So you may need to rewatch these steps, but I think that once you work on 1 or 2 problems, you'll become experts in epsilon delta definition.
Late to the party. So
Say it again?
now I understand.
Yeah.
Yeah, I came in late, so but anyway,
That's okay. Yeah,
I
so
understand.
we have 2 examples. If you go step by step and watch the video again, you'll have no difficulties. Very good. So let's move on. The next section is 2.5. Any questions for me? Of course, I highly recommend if you find anything in homework that you need help with, please bring it to class. So 2.4 is considered finished. 2.5. 2.5. Yes, please. Any question?
For, let's say, for example, we're given this on a test, and would we have to write every single step down? We can't skip one.
You cannot skip any step.
Okay. Sure.
Yes, please.
Do we have to commit the definition to memory?
Yeah, it's open notes, open book. You will commit it to your notes. Right? So yes, the definition has to be written. Yes, please. Okay, so let's continue with continuity. Continuity. So when is a function continuous? Here's a continuous function. Continuous. I graphed the entire function without raising my marker off the paper. Okay, in which way a function is not continuous? Not continuous. In several ways. Here is one. This is called infinite discontinuity. Infinite discontinuity. Here is another. This function is not continuous. It's called jump discontinuity. Here's another. This is called removable discontinuity. Discontinuity. So this, or it could be like this. So either the function is not defined at that point, or it is defined, but is defined at a different point. Both situations, this, or with a point defined somewhere else, not here, it's still a removable discontinuity. What is the property of removable discontinuity? Which does not exist, and why is it called removable? Okay, so here is the property. The limit, of course, this is A, and this is, of course, L. The limit as x approaches A from the left of the function f of x, of course, a function is f of x, equals the limit as x approaches A from the right of f of x. But it does not equal f of A. So this is the definition of removable discontinuity. Why is it called removable? Because I can remove it. By simply changing a finite number of points or x values where the function is not defined. I can have 1, I can have 2, I can have 3, but finite. So here is just, I only have to define this function in such a way that this point is moved here. So that is called removable. Here, I will never be able to bring them together because I have to change infinitely many points. Here, I will never be able to make this function continuous at this point because it's undefined at that point. So there is nothing I can do about that. But
so all continuous functions have a domain of positive, negative, infinity?
No.
Okay.
No. So for example, it's a very good question. So let's say tangent x, f of x equals tangent x. This function is continuous on negative pi over 2, pi over 2. So when we talk about continuity, I can also restrict the domain and say the function is continuous on this. This function is not continuous on all its domain, but it's continuous on whatever. So we have functions that are continuous everywhere, like polynomial functions. So which page am I on? I'm on 7. So we can say as a theorem, polynomial functions are continuous everywhere because that's their domain. But I can say rational, radical, logarithmic, trigonometric, etc. are continuous on their domain. Okay, next step here is something very important. I keep saying that. Everything is important, I know. Continuity at a point. So let's take a look. So here's a function. Is this function continuous at this point? Yes, because the limit from the left, the limit from the right, and the function value at that point, they all exist and are equal. I'm not talking about limit to exist. We are one step forward. So the function is continuous because the limit from the left, the limit from the right, and the function value at that point are the same. They exist and are the same. So how do we write this? Limit as x approaches a from the left of f of x, this is of course f of x, equals limit of f of x as x approaches a from the right equals L. F of a, what I meant to write f of a. So this is what does not happen here. The limit from either side, the limit from either side, left and right, they both exist and are equal, but they're not equal to f of a. So here, continuity at a point requires the limit from the left, the limit from the right, and the function value at that point to all exist and be the same. And then we conclude that the function is continuous at that point. Finally, before we look at problems, continuity on an interval. So what do you think? Anyone would like to give it a shot? When is a function continuous on an interval? When it is continuous at each and every what? Anyone would like to give it a shot?
Every point?
Of course. Of course. Thank you. So, of course, one other thing that I wanted to mention is any combination, addition, subtraction, multiplication, division, etc., of continuous functions is, what do you think?
Continuous.
Continuous. Thank you very much. Indeed. If I add two continuous functions, they will be continuous. So the new function will be continuous. If I subtract two continuous functions, the difference will be continuous. And the same thing with the function composition. Okay. And this is the theorem. I'm not going to write it because I don't need to write it. I can copy it for you. I just don't need to. The swapping of the operators. The reason it looks difficult to understand if you only at this point remember about the swapping of the operators. You see the limit of f of g of x and then f of the limit of g of x. So this is Theorem 8. This is an older edition of the book. I don't know which page to tell you in the book, but it's in 2.4. Okay, so now I will share my screen and we will pick problems, and then I have the intermediate value theorem before we conclude 2.5. But I want to share the screen and we can work on a couple of problems. So this is section 2.4, and then we'll talk about the intermediate value theorem. So here it is, 2.5. Let's see how I'm with time. Of course,